So, welcome to this session of lecture on analysis of guided structures. We are going to start this session of lecture with the analysis of the partially filled rectangular waveguide. Now, we had already found out the propagation characteristics of rectangular waveguides filled with homogeneous material. We found that the T to Z and Tm to Z modes adequately describe the mode spectrum inside rectangular waveguides filled with a homogeneous medium. However, unfortunately, the same strategy does not work if the rectangular waveguide is partially filled. So, the same strategy means the same decomposition of the fields into the T to Z and the Tm to Z modes will not work simply because of the fact that we cannot apply or satisfy the boundary condition at the dielectric air interface using the T to Z or Tm to Z modes. So, this is an interesting situation in which we have or we are in the quest for alternate mode sets, so that we can satisfy the boundary conditions of this this relatively complex problem. Let us go to the analysis of such structures. Let us go to the slides. Let us draw firstly the structure of a partially filled dielectric waveguide. For our axis, we will be retaining our original axis, which is x axis up, y axis in the horizontal direction. The waveguide is here, 0 to A along the x direction, 0 to B along the y direction. So, for the start we are going to stick with the axis nomenclature we used previously. So, this is the x axis, this is the y axis, this is my waveguide cross section, this is my waveguide. Along the x axis the dimensions 0 to A, along the y axis the dimension 0 to B. This is my dielectric strip, its media properties are epsilon 1 and mu 1, and the media properties here are epsilon 2 mu 2. So, this is my geometry now. In this case, if I apply the fields corresponding to T to Z and Tm to Z, we will find that we cannot satisfy the boundary condition at this interface. So, they cannot be used to satisfy the boundary conditions at this interface, and therefore, these are not valid mode sets for the problem. The question is, if these are not valid mode sets for the problem, how do we crack this problem? How do we solve this problem? The first step, as we all realized when we went through our potential function analysis and when we treated the case of finding the fields from the radiated by a source or finding the modes inside the waveguide, we did one thing, and that is we started from the potential functions and then we found out the fields. we applied the expressions of the fields, or we tried to satisfy the boundary conditions of the problem using those expressions of the fields. If we could satisfy the boundary conditions of the problem, then those potential functions which we selected are valid potential functions. If not, if the boundary conditions cannot be satisfied, we have to redo our homework. That means, our original choice of potential functions is wrong for the boundary condition under investigation. So, what we have to do? We have to choose an alternate potential function. So, there are in the rectangular coordinate system, it gives me 3 choices of potential functions. For this choice, we selected A equal to u z psi. That is how we came up or landed with the Tm to z modes. And when we chose f equal to u z psi, we discovered that the fields were of the T to z form. But one can also choose, as we said that time, that A equal to u x psi or A equal to u y psi. And we could use the same expressions of the electric and magnetic fields, which we found out due to the radiating current source in a homogeneous medium. Those same 2 sets of equations which link up the electric and magnetic fields with the magnetic vector potential or the electric vector potential, we can use those same two equations to find out the electric and magnetic fields in these 2 cases. And that is exactly what we are going to do. So, first of all, let us start with an alternative mode set. So, if this does not yield me the proper solution, okay, so we should be starting from another kind of mode set. So, let us suppose that the let us take the mode set which is Tm to x. Let us consider the Tm to x mode and find out whether the Tm to x, T to x mode sets allow me to satisfy the boundary conditions in this problem. So, let us take the mode sets Tm to x and Te to x and use these mode sets to satisfy the boundary conditions of this problem. If these mode sets allow me to satisfy the boundary conditions on the dielectric air interface, which is this interface, our mode set is a valid mode set. So, let us see whether the Tm to x or Te to x mode sets allow me to do that. So, first of all, let us write down the expressions for the Tm to x and the Te to x electric and magnetic fields. So, for the Tm to x mode, we have A equal to u x psi. Just like for the Tm to z mode, we started with A equal to u z psi. we call this equation 1. So, this is our starting point for deriving the field expressions for the TM2X mode. TM2X mode is transverse magnetic to x. That means, there will be no component of the magnetic field along the x direction, because the field is transverse magnetic to x. Just like for the transverse magnetic to z, there is no component of the magnetic field along the z direction. So, therefore, for the transverse magnetic to x, there is no component of the magnetic field along the x direction. So, we will discover that if A equal to u x psi, we indeed find out, or we indeed land up in a situation where h x component is 0. So, let us find that out. We can derive the magnetic field from H is equal to curl of A, which we already discussed before, and that becomes equal to del x of u x plus del y of u y plus del z of u z times u x psi, and that will be yielding ultimately minus u z del psi del y plus u y del psi del z. Note that the contribution of this and this will be 0. So, therefore, we find h x to be 0, h y to be del psi del z, and h z to be minus del psi del y. We call this equation 2. Next, we find the electric fields. So, our familiar equation which we know before is E is equal to minus j omega mu A plus 1 by j omega epsilon grad of divergence A. So, divergence A is del x u x plus del y u y plus del z u z dot u x psi which is A. So, that becomes equal to del psi del x. Okay, the other terms go to 0 because u y cross u y dot u x is 0, u z dot u x is 0. So, next divergence of grad A becomes del del x u x plus del del y u y plus del del z u z. Times divergence of A, which is del psi del x. So, that is del square psi del x square u x plus del square psi del y del x u y plus del square psi del x del z u z. So, my electric field is evaluated from these to be E x is 1 by j omega epsilon del square del x square plus k square psi E y one by j omega epsilon del square psi del x del y and E z is 1 by j omega epsilon del square psi del x del z. Similarly, so therefore, we see that the mode is T m to x because H x is 0, all the other components of the magnetic field are there and also the other components of the electric field are also there. Now, we come to the T e to x mode. For which f equal to u x psi. Just like for the T e to z mode, we chose f equal to or the electric vector potential to be equal to u z psi. So, for the T e to x mode, we would have f equal to u x psi, and T e to x means transverse electric 2 x, that means there will be no E x component of the field. The x component of the electric field will be 0. Let us see, let us compute the electric and magnetic fields. So, E is given by minus curl of F, it is given by minus del del x u x plus del del y u y plus del del z u z times u x psi. That is del psi del y u z minus u z u z minus del psi del z u y. Because these two terms are not going to contribute anything, u x cross u x will be 0. So, therefore, E x is 0, E y is minus del psi del z and E z equal to del psi and E z equal to del psi del y. Let us call this equation 4. So, you see now that E x is 0 corresponding to the transverse electric to x mode. So, for computing the H fields, we use H equal to minus j omega epsilon f plus 1 by j omega mu grad of divergence f. So, divergence f is del del x u x plus del del y u y plus del del z u z dot u x psi. That is del psi del x. because these two terms will not contribute anything. U y dot u x is 0, u z dot u x is 0. So, now grad of divergence f will be del square psi del x square u x plus del square psi del x del y u y plus del square psi del x del z u z, del square psi del x del z u z. So, from here my magnetic field components work out to be H x equal to 1 by j omega mu del square del x square plus k square psi H y equal to 1 by j omega mu del square psi del x del y and H z is 1 by j omega mu del square psi del x del z. So, let us call this equation 5. Thank you. We will be continuing in the next lecture.